Substitution in indefinite integrals. Well, actually, the method works for definite integrals as well, but we'll get to that at the end. I want to tie together indefinite and definite integrals. If you're like, I still really don't know the difference, by the end of this, you will. Okay, so we did this exploration yesterday. Substitution in indefinite integrals. There we go. In order to evaluate an integral, we occasionally, I don't know about occasionally, we often use this. Substitution is a very common method when an integral gets a little bit complicated on us. We often make a variable substitution, often called U substitution. I don't know why. We just always seem to use U when we do this. You've had a taste of this before back in when we were doing regular calculus, where we did some U substitution. Similar procedure. The substitution can turn an unfamiliar integral into a familiar one that we can easily evaluate. That's the big move of substitution. When you run into an integral that actually is easy, if you could look at it the right way, but looks hard because of all the stuff that's going on, U substitution can simplify the issue down for you. An example. My previous ink notations are on there still, so we'll have those up there. I'm going to do the first example really quick, and I want you to see what it does. Don't get focused on the individual details, because after I do the first example, then I'm going to do like, how many more is there in the note? 4, 7. I'm going to do it like 9 more times. Yeah? So don't let this freak you out when I do this one quickly. I want to get you the feel for what this thing does. So evaluate integral of sine x times e to the cos x. Do you see how complicated that looks? At first glance, when you look at it and this cos x is up here, it's going to freak you out a little bit when you run into ones like that. So here's what U substitution does. Again, deep focus on what it accomplishes, not how to do it. We'll get the how to do it in a few minutes. Solution. Go over here in a box and we let U equals cos x. How am I going to know to let U equal cos x? Don't worry about that. I'll get to that in a second. Just imagine. If somebody let U equal cos x, then find the derivative of your U that you've got here. U equals cos x. I'm going to go du dx equals negative sine x. Major hint about why we chose this. Look at the negative sine x that just popped out of there. Yeah? So if you're really trying to understand what's happening here, look what just popped out of there. The sine x did. Now, this is du by dx. Over here is just dx. So I move this thing around until I get dx. So du dx can be broken up like this. Du is equal to negative sine x dx. All I did was solve for that du. We did this once before, where we went, this Leibniz notation allows us to take du and dx and break them up as we need to and move them around. Totally legit. Now if I use everything I got over here, watch what happens. It's beautiful what happens. E to the cos x will now be e to the u because I'm replacing cos x with u. Better yet, sine x dx gets replaced by du up to a constant. The constant out here is -1, so you got to play with the constants. I'm going to show you how to handle the constants. So you go, okay, I just do this with the constants and everything's going to be fine. In the PowerPoint, they just sort of plug it in there like it's so easy. There's my integral. All I did was switch the order here so you could see it a little bit better. I switched the order of e to the cos x sine x, and I put the sine x with the dx. I'm like, I know sine x and dx ends up going together, so I put them together. So I didn't really do anything in that line. And then I put all the subs in. Right there. This is the line I want to talk about. E to the cos x became e to the u. Sine x dx became du, except a negative popped out of this whole thing. Okay? This shows all the steps in between. The way I'm going to show it is going to be a little bit more, I won't say easy, but it'll be more recipe-like. Just do this and the subs will happen. Now, we are focusing on what happened. A very tough integral became something pretty nice, actually. Why does it happen? Well, it happens when the chain rule produces the factor out front. You're like, well, what are the chances of that happening? Pretty good, actually. It happens a lot where the chain rule produces the factor that you got out front. Take a look at this for a second. The derivative of e to the cos x is e to the cos x times sine x. Well, I know there's a negative, and the constants we're going to have to get used to. And you see all the time in textbooks, they'll say up to a constant. They just go like, well, the constants we'll take care of. We don't worry about the constants too much. I mean, we're very worried about them. We got to get them right. But it shouldn't be a big problem handling those constants, really. This integral is easy. The integral of e to the u is e to the u plus some constant. And then at the end, you go back and say, well, this was a question in x. Now I'll go back to x. So it's e to the cos x plus c. Many questions that can be done by substitution, if you could look at it very carefully, you might actually be able to do it without substitution. But I'm telling you, do them with substitution. Reminds me of the first day of product rule, right? We did some product rule questions that we probably could have just multiplied out. But we practiced on them so that when the tough ones came, we were ready. So practice these things using substitution so that when the tough ones come, you got a procedure that you can do. I will pause for questions here, even though it was just supposed to be an introductory one. Do you have any questions about this procedure? Personally, I think the only tough part is the start. The rest of it's sort of a recipe, actually. You let u equal something, you take its derivative, and you sub it in. There'll be some playing around. I'm not saying it's going to be quite as easy as I'm saying, but there's sort of a procedure here that we're going to follow. The questions you probably should have are, how do we know when to do this? Yeah, that's where I'm going to start my other part of the lesson. And how do we decide upon the substitution to be used? Because those are some mysteries here. And so I'm going to build that as we go. So I've got an extra page over there, and I think it's just examples from there, right? Just a whole page of examples from there. So I'm going to go over to my flip chart, and I'm going to keep coming back to this page. Because as I'm doing them, we'll start adding on to how do we know to use this, and how do we decide upon the substitution. So keep reminding me. If I forget, you're like, okay, put that over there. Everything I say about this as we go. We'll just start doing some, and we'll go from there. First example, integral of x cubed times cos of x to the fourth plus 2. Here's what my brain sees. This is what I want to teach you. My brain sees that if I went to take the derivative of cos of x to the fourth plus 2, I'd get sine, yes? But then when I did the derivative of the inside by the chain rule, I'd get 4x cubed, and x cubed's right out there. And my brain lights up like, oh, that's good, it's out there. Up to a constant. I know there's a 4 there. I got to deal with the 4. I totally get it. So what I go over here and I go, let u equal. And I'm pretty excited because I got let u equal x to the fourth plus 2. And I want you to help me with the previous page in a second. I'm going to go du dx here. I'm going to take the derivative of my u, which is the second step of substitution. Decide on a u. Take its derivative. I'll admit that sometimes it's trial and error. You're like, oh, I'll just try this u, see what happens. But here, it bears fruit immediately. I go du by dx equals 4x cubed, and I'll put it to u. Why is it? I'm going to put a little smiley face beside that. Or if I was really good at drawing, I'd draw a pizza over here to go, oh, I can order a pizza now. It's all going to be fine. Are we far enough along? Can you tell me what it is about this derivative, du dx, that tells me everything's going to be fine? Luke? It's x cubed. And the coefficient, hopefully we're learning, the coefficient's not going to be a problem, but it's x cubed, and that makes me happy. So let's go back to this other slide and say, how do we know when a substitution is required? Well, one way we could know is chain rule of one part produces the other part. And I didn't really use fancy language there because I really want it to be accessible to you to say, when do I know? And then I'll put up to a constant. Boy, that phrase they love in textbooks. Up to a constant. And what they mean by up to a constant is like, well, I know there's a 4 out there or a 2 or a negative, but we'll deal with that as we go. And in a minute, I'm going to show you exactly how to deal with it. So it doesn't have to be fancy or difficult. I'm going to show you exactly how to make sure the constants work out. How do we decide upon the substitution to be used? One way to know what to use is let u be the inside of one part of the integral. Do you know what I mean by inside? Because we kept saying in chain rule, we said times the derivative of the inside. And in the example we did, there was definitely an inside available to us, and the inside was cosine, the inside was x to the fourth plus 2. So that's one strategy, is let u equal that inside. In fact, I knew people that were like, as soon as they got one of these, they just immediately let u equal the inside of something and see what they got and go, okay, does this help? It's a great strategy overall. Okay, step 3. Okay, I'm back to here now. Step 1, let u equal something. Then du dx to get du and dx over here. Then I say isolate du. So over here, isolate du and go du equals 4x cubed dx. I'm well on the way. But 4x cubed dx isn't what I really wanted. So this is what I do. Textbooks, the last example showed it a little different. I underline what I'm trying to replace. X cubed dx. And if you want, you can rewrite it like this. This is what the PowerPoint did, is it rewrote this like that. And see, I put a little space there. I can remember doing this now. You just a little space to go. What I'm really after is x cubed dx. That's what I want to go away. You're like, what about the cosine? Oh, don't worry about that. That's going to be fine. I want to deal with the x cubed dx. So over here, I isolate for x cubed dx. Solves all my constant problems right there. I go, no, I'm replacing x cubed dx, so I'm going to move the 4 over there, and x cubed dx is 1/4 du. Yeah? I don't see that in a lot of textbooks, that way of handling it. Okay, here's the big moment. Stick with me. If you're only going to stay awake for 90 seconds this lesson, I think this is the 90 seconds. How do I put all this stuff together? Integral. Cosine, not x to the fourth plus 2 anymore. U. Yeah? And maybe that really helps to understand why this method is so good, is instead of having this crazy inside that's messing everything up, I'll just go, let's just imagine we'll just call that u for now. Then, x cubed dx. I'm going to write in red here, okay? So you can see where I put everything in x cubed dx. I want to replace x cubed dx with 1/4 du. 1/4 du. I like that. I like that move.
So the point is that the 1/4 is coefficient. We can put that on either side.
Yeah, keeping it in the integral, that's fine. But it's much easier just to go, just push it out front and make my integrals, and then it's not a battle anymore, okay? Now, on a scale of 1 to 100, if you're about a 22, we're in great shape, because now I'm going to do this 7 times in a row and do all that thinking again and again and again. If you're like, okay, I sort of get the gist here. There is sort of a recipe here. I won't call this a recipe method, but there is sort of a recipe. Once you've decided it is substitution, that's what we really got to work on. How to decide when to use this. Because the rest is a walk in the park, yeah? Like you're literally picking up a slice of pizza and eating it while you're right now. It's like, this is done now. Integral of cos u. Oh, and on the back board, I've built your trig table there. That will be up for the test. All the trig derivatives that we have so far, I encourage you to memorize them. It makes your homework easier to just sit down and memorize them if you haven't already, because things will go fast. You're not always looking them up. But you don't have to lean on that. Come test time, you can be like, okay, which one? Yeah? Question, Luke.
Doesn't our cos have a -1?
Oh, yeah. Yep. Right there. Thank you. He's already got them memorized, does he? Or maybe the way we learn them helps to go, oh, I remember that cos is the -1. And I got arctan coming up for you today at just the right time. Okay, here, the rest of this is supposed to be easy. 1/4 sine u.
-1/4 sine u.
Oh, is it?
No.
Exact right thinking. You got to see inside his brain, it's the exact right thinking. Is it positive? Is it negative? Yeah? So then you go, oh, well, let's see. Derivative sine u is cos u. Okay, it's good that way, okay? And then the plus c, right? Not quite done. What's the last step? Bring the u back, yeah? We can use u's to get our answer, but in the end, we have to answer with x's. again, you might get good enough at these that certain ones you're like, oh, I don't need substitution. I can see what has to happen here. And that's fine, but I encourage you to do everything in the homework today with substitution so that you get so good at it that when you need it, you can do it. Notice if this was a definite integral and there was an a and b there, like a 1 to 3, the next two steps are just sub in 3, subtract sub in 1. You know what I mean? So the definite integrals, you just finish those off. You can see why we're practicing with indefinite integrals, because those last two steps are just sub it in, sub it in. Any questions there? Let's look at another one. Integrals root 2x plus 1. And you know what? Any of these ones that have an inside like this, it's awfully tempting just to try it and see if this helps. Let u equal 2x plus 1. Just let u equal the inside of whatever function. The part that would have to be chain ruled. And so then, okay, does anybody remember now? I'm going to get the recipe part of this down so we can focus on the thinking. What's the next move? Once I choose a u, what's the next move? Find du dx. I know what you said. You said find du, and you're right. The step to do that is du dx. Then go du equals 2 dx. Here's what I do. Then I look over here and I go, what am I actually replacing? And the answer is, I'm only replacing dx in this particular question. If you don't know what I mean by that, you'll see in just a second. So I isolate dx. It helps me over here. I'm going to write it in red. This is my take on this, is I'm going to solve for the dx that I know I have to replace over there. And that solves my coefficient problem. I don't have to play around with coefficients quite so much if I'm subbing right in what I want.
What would happen if you were to try and put 2 dx in there?
It does work. It's just that you've got to, some textbooks will do this. Their next line will be 1/2 root 2x plus 1 times 2 dx. They set it up over there. They go, okay, I'll get a 2 in there, prepped to go, so I know it's a 2 dx that I'm replacing for. I don't really like it. I think mine's way better. And mine doesn't have a weakness. It's not like, oh, well, later on you find out that mine has a problem with it. I think this is the way to handle it.
So we're trying to make the x coefficient equal 1 for sure.
No, I don't know. Because maybe the next question it says x dx. Get what you need over there. Go over there and say, okay, all I got is dx this time, so I'll solve for dx. Yeah?
Okay.
And then you'll see that method will expand a little bit. So then what I get over here is integral square root u. Isn't that nice? Look at that for finding integrals. Doesn't have a 2x plus 1 there. Takes all the confusion out of it. And then replace dx with half du. Watch what I do. I'll do it in red. Replace dx with half du. I like taking care of it right there. Get that coefficient out there. And so now you understand a little bit more. It says up to a constant. You're like, okay, I got a constant. I know. I'm not particularly worried about the constant. It's going to end up out there anyways. Then you pick out a slice of pizza because the rest is home free, hopefully. But you know, our integral experience isn't huge now, so I'll go through the steps. Let's see, 1/2 integral of u to the 1/2 du. Now the antiderivative of u to the 1/2. Let's see, add 1 to the exponent, u to the 3/2, and then divide by 3/2. But I don't do that. I got to be honest with fractions. I don't do that. I just put the flipped fraction out front. That's the pizza I need. There is the 2/3, because 3/2 times 2/3 is 1. You know. Plus c, and then a little simplification here. 1/2 times 2 is 2/6. This is 1/3 u to the 3/2 plus c. Yeah, not done. What else? Bring the u back, yeah, or bring the x's back. So I get 1/3. U was 2x plus 1. But this is Really should go back to the radicals. But I don't think any time this year I've been too uptight about that, you know? I'll let your first year prof hammer you on that, you know, if that's what they're into, you know what I mean? It really depends on what's going to happen next. If we're going to take another derivative here, this was a mistake to go back to square roots. If we're going to sub into this, you have to do this pretty much to get ready to, you know, so it really depends on what's going to happen next, how you're going to leave that, okay? But I want you to prepare for what the answers in the back of the book might say. Oh! Plus C, okay. Questions? Do I have to add anything on to my notes there at the start? It said, how do we know? Chain rule of one part produces the other part. Or, let's add to that, I think. Or, no, I got it right there. I don't have to add on to it. Okay. Let u be the inside of one part of the integral. If you're just not sure what to do, let u be the inside of something and see what you get. So I'm trying to leave this open that it's sort of a recipe, but sort of a, I don't know, trial and error. Try it out. See what happens. Integrals are like that sometimes. Let's do another one. Who wants a shot at u? That's a weird way to phrase that, isn't it? Who wants a shot at u? Let u equal. How do I know this one's a u type question? There's two ways to know, I think. Luke?
You got a chain rule, like one of the inside terms is
Yeah.
and the coefficient x squared.
He gave both answers in one. There's a chain rule going on here because there's an inside. And when there's an inside, you're like, maybe use substitution. And then I'll do the second part by doing the chain rule and really producing something that you hopefully can see that this one is rigged up for substitution. So if I let u be the inside of that thing, 5 plus 2x cubed, when I do my du dx, I get 6x squared, and now I'm jumping up and down. You know? And if you saw it before, even better that you saw, oh, when I take the derivative of the inside, I get the outside. This is an anti-chain rule if you want. We're undoing somebody's chain rule is what we're doing here. And so then I get this. And so now my move is to solve for du equals 6x squared dx. But that's not what I want. And the PowerPoint rearranges it. I don't always rearrange it, so I'm going to try and do better and rearrange it. And I'm going to write just a little space there. Just to go, here's the way my brain is thinking. I got this square root thingy that I'm not too worried about, because I just let the inside equal u, so that's going to be nice. And then I got to deal with x squared dx. So what I do is I go back over here and go, what I really want is x squared dx. This is 6x squared dx, which isn't what I want. So I'm going to isolate the x squared dx. And I was doing that in red before, wasn't I? Let me do that in red so you can really see what I'm up to. This is 1/6 du equals x squared dx. I love that move. It just makes my substitution so much easier when I go, I know what x squared dx is. Now watch this step here. Equals integral of square root of square root of what? U. Isn't that nice? You know, when you let u equal the inside, you end up with a nice function, not a chain rule type function. You're like, where's the chain rule? It's over here. Yeah, I'm taking care of the chain rule, but I'm just sort of taking care of the chain rule separate here. And then x squared dx gets replaced with, I'm replacing x squared dx with 1/6 du. So I put the du here, and I put the 1/6 over there, and I'm extremely happy with my new function, or my new integral, because it's a lot simpler to deal with. If you're really with me, you could look back and go, I think I can land it right from here. Now that I've seen what's going on, I think I can handle it right from here and jump right to the end. Okay, maybe. On really easy ones. Yeah, but practice with the easy ones. This method, so when the hard one comes up, you know what to do. The rest of this is pretty straightforward stuff. I hope. If it's not, you let me know. Is that I need to go u to the 1/2. Well, this is a lot like the previous one, isn't it? It's a u to the 1/2 again. 1/6. Let's see. Increase the exponent by 1. Then divide by 3/2, I guess. But that's not the way I think about it. I just go, okay, well, if 3/2 is going to get multiplied here, what I really need is 2/3 there waiting for it, so that it comes out to 1 and stays what I want it to be. And then a plus c. And so I'll draw a little line here because I got to go a little farther here. Let's see, 1/6 times 2/3 is 2/18, which is 1/9. Jacob, question?
Why is it plus
I don't know. I went to write a C. I think I even said C, didn't I? And then wrote 6. This is what you have to look forward to, folks. 41 is the number. You'll start going, what is going on here? Random stuff coming out of my brain. Good news is all the good stuff's still in there, just details sometimes. Okay, that's why you're here. You guys are here to keep an eye on that. 1/9 u to the 3/2. Can I handle it right now? U to the 3/2. Where's u? Where are you? Where are you? 5 plus 2x cubed. But I want, I don't know, maybe I want this. Maybe I want it square root cubed. It depends on what you're doing next. If you're doing another derivative, don't do this. That's insane. But if you're subbing in now to find, putting in an x or something like that, you're going to want it like that. So I'll show that version of it. I'll draw another line here so you can see what I got there. How did I do? 1/9, 5 plus 2x cubed to the 3/2 plus c. Yeah, everything's good. Great stuff. Oh, geez, we're cruising through these. I don't remember cruising through these last year. There's more questions or something. But I think I was more careful with u substitution earlier when we did it, so that now it doesn't seem like it's so weird what we're doing here. Do you have questions, though? Did I do anything different there than my advice says? No, let u be the inside. Yeah, that's often what the u substitution comes from, is let u be the inside. But you really want, when it works well, is when the derivative of the inside is in the outside. Yeah?
So the inside term is substituted by u, and dx and all other terms should be substituted by whatever.
Yeah. And if you start to get that feeling like, well, it's sort of got to be rigged up properly. Yeah, I know, but we're adding weapons to what you can do. So remember when I taught you product rules, two things multiplied together? And you're probably impatient at that point. You should have been like, yeah, but what if it's a quotient? Like, okay, I know. We'll do quotients. We'll do chains. We'll do all these things. We'll mix them together. And here's one weapon for now. And then I'll give you another weapon as we go along. So here's one weapon. If you can see the derivative of the inside in the outside, substitution's there to help you out. Substitution does a lot of other things too. There's other options for substitution, and I'll do a few of those coming up. Ooh, okay, so here we go. You know what? I'm going to try and switch it over to you because we're getting late in the examples here. We got to start thinking about it on our own. What is it about this question that tells you that substitution might be helpful? Well, the denominator is a tip that maybe substitution is helpful here, but there's a little bit more to it. There's something about this situation that tells me that substitution is going to bear fruit.
There's like a root with something inside.
Yeah, okay, so level one. Level one is, as soon as I've got a chain rule going on here, maybe u substitution can help. Can anyone see a step farther to know that u substitution is really going to help here based on the derivative that we're going to get out of it? John? Yeah, this degree is one more than that one. So when I take the derivative of this inside, I'm going to get negative 8x, which is x, up to a constant. Again, the constant is not a pressure situation at all. We're going to handle that in the details. So then, you go over here and you go, let u equal 1 minus 4x squared. So du dx is negative 8x, which is a little bit troublesome because it's not x. Wouldn't it have been nicer if it was just x, but we can handle that. And then I go like this. Du equals negative 8x dx. And then me personally, I just stop at that moment and go, okay, is this what I really want here? And the answer is no. What I really want is x dx, and I'll underline those in red. I'd really like to replace x dx, not negative 8x dx. So me personally, I deal with those coefficients over here. I go, okay, what I really want is negative 1/8 du equals x dx. Oh, I was doing that in red. I keep forgetting to do it red. So you can visually see what I'm trying to accomplish here. Negative 1/8 du equals x dx. And if you're not sure why I did that, just take a look at what happens over here as I go to do this integral. Integral, and we'll do one piece at a time. We'll do the denominator first, okay? The denominator is square root. That's the part I went after. 1 minus 4x squared. That's the u. There, that's a better looking integral now. Maybe that's the part to really understand here. Oh, isn't this nicer looking? Root u. I know it's in the denominator. We'll have to deal with that in a second. Then I took care of what's in the denominator. That's all taken care of now. Now I have an x dx to deal with. Well, I nicely did the work over here to get x dx by itself. And so I need a negative 1/8 du. Here comes the negative 1/8 du. Negative 1/8 du. Well, what goes in the numerator? 1. You know, like, that's not, just because I divided it by 1 doesn't mean there's not still a 1 there, you know. Reminds me of when you cancel 3 over 3. 3 over 3 doesn't really cancel. It divides to give 1, you know. So. Questions there because the rest is a little more straightforward. Question?
How did we get 1 in the numerator?
Well, let's just talk about cancellation for a minute and factoring things out. When you factor things out, negative 1/8 out of this thing, what you're left with is a 1. Picture this one. This maybe is the helpful one. 3 divided by 3. No, I want 3x over 3 over 3y. This one comes up in grade 11 sometimes. And then they cancel and they go, okay, 3 and 3 cancel. And so what I get is something over y. What's the something? What's 3 divided by 3? 1. Yeah? So we didn't really cancel these things. They didn't disappear. We just divided them by themselves and ended up with 1. Yeah?
What did we divide originally to end up with 1 in this?
Yeah. Okay, now the rest, well, we process that, equals negative 1/8. Let's see, integral u to the negative 1/2 du. There, that's better for finding antiderivatives. Add 1 to the exponent. So that's 1/2. Then divide by 1/2, or just know you need a 2 out there. And so I get negative 1/4 square root 1 minus 4x squared. And my brain's screaming something's wrong. And I don't know what it is, so I'll just let me think about it for a second. No, it's right. I don't know why I thought something was wrong. Overthinking, I guess. Well, what questions do you have? There's one that's tougher to land. Like if you, even if you saw what was about to happen, it's tough to go from here to here. You really need substitution to make that play out.
Kind of off topic, but like, what happens if the degree of the u is high, like 2 more higher than the
It's a little hard maybe to see what my answer is, but what you're asking is, well, what happens if it's a quotient? I'm like, well, we're going to need something else. Clearly, this doesn't solve all integral problems, and there's a reason why there's whole courses of integration. You know, just learning how to do integrals. This is one weapon in the fight, and you're right. As soon as that degree goes up by 1, some other strategies are going to be needed. Yeah. This strategy is specifically for when the derivative of the inside is there on the outside. It happens shockingly often, weirdly, is that it comes up a lot. It also handles other situations, which we're going to see in a minute. This isn't the only situation that U substitution handles. Other questions there? Sometimes a trigonometric identity is helpful. You're like, oh, good. I'm so glad trig is back. Well, there's a lot to talk about here. Integral dx over cos squared 2x. And I spent a lot of time thinking over this over the last couple of days going, what should I say here to help you to know what trig substitution should I do and when? Because we didn't beat you to death with trig identities in grade 12 like maybe we could have. You know, in other years, sometimes we really beat to death identities because we had enough time. We didn't do that in your case. It wasn't as bad as the previous year. You should have seen the first year of coronavirus. I had to teach trig identities in the middle of all this because we hadn't done any trig identities in advanced functions. And I thought about it, and I finally had a brainwave. When you see integral of cos squared 2x dx, notice I put the dx up top there. Maybe it should be 1 over there and a dx out there, but you'll see this sometimes where they just put the dx up top. You go to your trig table in your brain, hopefully, and you go, is there one of these over there? You look on the right-hand side of the derivative table over here and you go, okay, well, I need cos squared. I'd really like to take the integral of cos squared here. Do I see any cos squareds here? No. Sort of. Okay, no. And then you're like ready to give up. And that's where trig identities are over there. Your trig toolbox is over there going, me. I can help. Let me do something. I can help. You're like, well, what do you mean you can help? I'm like, well, cos squared could be many things. It could be 1 minus sine squared. Is there sine squareds up there? No, that didn't help at all. But there's another one. Cos is something else. What else is cos on the trig toolbox? Yeah? That's the kind of thinking that has to go on with the trig toolbox. Let's go through and go, what options do I have here? What could cos become? Cos could become secant. Better yet, 1 over cos squared is secant. So I'm going to just put a couple of lines in here. I think that line is shockingly helpful because then the 1 over cos squared is right there and you're like, oh, it's secant squared. And at first glance, it's like, so what? You switch to secant, goody. But then your trig, your list, and why having them memorized is so important is to go, well, I know I could do secant squared. And in fact, it's an easy one. Secant squared, the integral of secant squared is tan. No, I'm going to stick to my rule. Even though I know what to do here, I can just write down the next line. Maybe you can. Maybe you don't need u substitution here. I'm going to stick to practicing u substitution to be ready. Okay? So over here I go, okay, so let u equal 2x, du by dx equals 2. Du equals 2 dx. I'm just trying to replace dx, so I'm doing 1/2 du equals dx. There it is with substitution. I did that quickly on purpose to maybe speak to some of you who are like, okay, well, if it's just a 2x inside, maybe I don't need u substitution. Maybe I could just land this integral. Maybe I could just be over here, forgetting all this for a second and going, no. Jump down, how many lines do I need? Boop, down here. Maybe I can just go, well, I know it's tan of 2x to get secant squared of 2x. But then there'll be a 2 that pops out, so I need a 1/2 out there. Yeah, maybe it's possible to just go, okay. Yeah. And actually, I think there's ones like this in the homework where it's like, you didn't need u substitution to do this. But I encourage you to practice it so you have the method down. Here's practicing it. Secant squared 2x stays there. And so I go integral secant squared u, and then dx is 1/2 du. And so then I get 1/2 tan u plus c, and then I put the u back in. Okay? I tried to do 2 at once. I hope I didn't confuse you. I tried to do 2 methods at once there, which is, yes, I can do the u substitution, but there are times when that inside is pretty simple that maybe I could do it without the u substitution. Do you have questions, though? That wasn't the big point of this question. The big point of this question was, when you get a trig, that one that you don't recognize, look at your trig toolbox and see if there's a way to switch over to something you do recognize. A couple more like that coming. Yeah, 2 more trig ones? 3 more trig ones total, actually. Do you need more time there? I don't know if I've set this up right and given myself a separate page for each. I haven't. So I want to duplicate this page. Just give me 1 second to get this, a couple more options here. This page, duplicate. That page, duplicate again. 3 copies of that page now. So now I can clear that one. And clear that one. So I think it's right now. There's the example I just did. But I think I've given myself, there we go. Okay, so now I'm doing F. Integral of cotangent squared of 3x dx. Oh, this one's tough. We've jumped from level 66 out of 100 to level 218 out of 100 here. Cotangent squared. We look at my trig toolbox and I go, or I look at my trig derivatives and I look for cotangent squared up there and I'm like, there's no cotangent squareds up there. There's cos and sine and secant squared and secant, tan, cosecant, cotan, cosecant squared. Manny, what do you say? You got this or no? He says no. He says no. Manny has this one over here. He jumped in. I'm going to do my tan derivative in a minute. This is all Manny over here. Manny was like, oh, I can help you, Mr. Todd. He's got this. So what I'm going to try and do is help Manny and everybody else jump to a whole new level of trig identity management. I'm going to do what I just over there. But sine squared y, sine squared x plus, no, I better use y here, or else things will get a little confused maybe. Sine squared y plus cos squared y equals 1. But we want cotan squared. That doesn't have cotan squared. Would you agree that doesn't have cotan squared? I want to make it have cotan squared. See, Manny's identity over there and the identity I need here are all the same identity. It's all sine squared plus cos squared y equals 1. But you got to do something. What are you going to do?
You can just put cos squared over sine squared for cotan squared.
I'm going to rephrase what he said. I'm going to divide everything in this thing by sine squared. And how did I decide on sine squared? For the reason you said, is that I want cos squared over sine squared. Yeah. Does this always work? No, nothing always works. But it could work. This might help. Sine squared divided by sine squared. 1. Cos squared divided by sine squared. Cotan squared. And 1 over sine squared y. Cosecant squared y, and then my brain starts jumping up and down because I go back to my trig list here and I'm like, wait a minute. Cosecant squared's out there. Yeah, cotan's not out there, but cosecant squared is. Okay, so settle down and find cotangent squared in all this. Cotangent squared y equals cosecant squared y minus 1. Therefore, the integral of cotangent squared of 3x is equal to the integral of cosecant (3x minus 1) dx.
Why did we use variable y for that?
Because I didn't want you to get confused between this x and this x. Yeah? By using y, hopefully you could see the jump there, that here the y is 3x. break that into two integrals. Cosecant squared 3x dx minus integral of 1 dx. Now, I don't know. Do we need to use substitution at all here? It's just a 3x. Yeah, and I know earlier in the lesson I was telling you, practice them. And you should. What we should do is go, let u equal 3x du dx equals 3, du equals 3 dx. So 1/3 du equals dx. That's definitely what we should do. But I'm going to start talking to you about the possibility that maybe we can jump ahead here. Anyways, I'm going to finish using it. Equals integral of cos squared u du, and I need a 1/3 up front. This one I don't need anything special over there. Luke's going to have a question in a second. I'm going to refuse to answer it for just a minute, okay? I'll rewrite it so I draw his attention to the question he's going to have. Cosecant squared u du, and I can do cosecant squared is negative cotan. Luke, I know you got a question. Or you should have. Of all the times I need you to have a question, now's the time. Buy myself a little space here to finish this question off, and then I will pause for questions. Negative 1/3 cotan u is just 3x. And I played some games there with the c's, and we got to talk about that too. Questions there?
Okay, I get where C2 came from, but then how did you go from plus C2 and plus C1, just plus C?
Yeah, good. I'll do it with c's first, and then I'll do it with numbers. All right? I'll pretend I know the c's for a second to help you. I did this integral out of here, and that integral produces a c, and I'll call it C1, because I knew what was coming. More c's were coming. Then I did this integral over here, and it produced a c, C2. And I said, well, okay, they're just constants. I'll put them all together as one constant called c. Let's say it was a 5 and a 3, and this constant's 8. So mixing constants together and giving them a new name is no problem. You're like, well, it is a problem. Where do I sub in? I'm like, yeah, don't worry about it. It's totally going to work out fine combining constants. You just got to know where you're subbing in and which constant you're solving for. It's not going to be a logistical issue. Some people don't even do that. They just call it C, and put a C down here and go, it's C, all right? It's a constant, I know. But this is technically the way you should handle it, is give each constant its own name. Yeah? Questions there? How many more do I got to do? Go. Time's becoming an issue here. Oh, cos cube's much easier. Okay, much easier example coming. More time? Integral cos cubed x dx. I'm just going to do this one and see what you think. Cos cubed is not on the list. In fact, there's no cubes whatsoever up there. Cubes got to go.
We can make it cos squared.
Yeah, cos times cos squared, which is not helpful, but this is. I turned that cos squared to 1 minus sine squared. And the reason that's so helpful is because the derivative of sine is cos. Let me do a little work to help you see it. I'm going to put this one up at the top. Here's the line I want you to focus on so you can see what I can see here. I distributed this cos x in there, which broke this thing up and gave me a cos x integral, which I'm not worried about at all. And then it gave me a cos times sine squared integral, which was great news. Because the derivative of sine is cos. I can go up here and go, let u equals sine x, du by dx equals cos x, du equals cos x dx. It's the easiest substitution yet in some ways, except that you got to see through the trig. So over here I get sine x plus c1, and this is minus the integral of u squared du. I'm not acting like that is easy. Stare at it long enough where you go, oh. Because that's one that comes up all the time.
So now,
I'll finish it off and give you time to process and come up with lots of questions. Making sure I haven't forgotten any details there. Hey, I'm acting like this is so easy. No, I'm not trying to act like it's so easy. I just want to keep this lesson moving and find out what your questions are. Which step do you want to talk about? You want to talk about the C's? Each integral produces its own C, and I don't care that they each got their own C. I'm going to make it into one giant C over here. Yeah? What's your other question?
when you put u squared du, you found the antiderivative of that first before making it x. Is that like a general thing we should do?
Absolutely. It's much easier to do this antiderivative than this one.
Oh, yeah.
Not impossible to do this one, but this is way easier.
Okay.
Then put the u back in afterwards.
So the du only applies to the cosec sine squared?
It worked out great this time. Du was cos x dx, and that was that whole thing right there. I didn't have to do anything special there. It was laying right there as the du. So cos x dx was du. This was u squared, and life got incredibly easy very quickly. This happens with trig sometimes. If you get the u substitution in trig, all of a sudden a really tough question becomes pretty easy. Was that your question?
Well, there's another cosec dx.
Oh, yeah. That's good. That's really good. The u I used, and it's the reason I did this one right here, is I went, whoop, let's just get this one done, because I let u equal sine x, and it's like, okay, well, is that a u over here? No. The u I used, oop, that's red. I want it in yellow. When I used u, I only used u over here. Yeah? Over there, I was like, I don't need u over here. You stay over there. Yeah? Good. And that's why I landed it right there. I was like, let's not get confused about where the u applies to. I only needed u for the right-hand integral. The left-hand integral didn't need any help. Other questions? Was that was the last of the indefinite integrals. Now we bring back definite integrals to go, okay, that's fine, but I thought this was about area under curves. And if you want, this is all just practice on antiderivatives. And now we'll go back and do a couple of ones that have limits of integration. Let's talk about what substitution we do. We want to let u be something where the derivative of it will be in the other part. You really want to let u equal secant x, and it does work here, actually. letting u equal secant x will work here. But there's another option here. And I want to show it to you one time so you can see it. I'm going to let u equal tan x, and if you're wondering why, watch this. And this comes back to the trial and error nature of substitution sometimes. Sometimes you just got to go, well, I don't know which one to let u equal to. So I'll just try one. I'll let u equal tan x. And great things happen immediately because du dx equals secant squared x. And you're like, aha, beautiful. Yeah? So there's not always a right way to do it. There are many right ways to do it. By letting u equal this one, du dx became that one. Isn't that nice? And so I solve for du equals secant squared x dx. And everything goes wonderfully here. This is integral from tan x was u, secant squared x dx was du. Look at that. Beautiful. Beautiful. So I don't want to leave that out in this lesson. So sometimes you just got to go, I don't know. I don't know what substitution to do. I'll let u equal this one. And as it turns out, if you let u equal secant x, it works out as well, but it's not quite as easy.
I just thought of something. How would we find the antiderivative of tan x? Like, we know how to take the derivative and get it to secant squared. How would we find the antiderivative?
That's a great question.
Oh, for later.
It's like, calculus is like this. Every time we're like, okay, there, now we're good. And you're like, and go, oh boy, we still haven't done the antiderivative of tan. You know what I mean? Like, so there's lots more to come in. One problem though.
That's very lower though.
Where did the other secant squared go?
Secant squared dx is du. How nice was that, right? There's a problem.
Your upper lower limit.
Oh, I didn't put the upper and lower limits here because this said use x values 0 and pi over 3. Uh-oh. These aren't x values anymore. We need u values. Do you remember this from way back when? When we did u substitution, sometimes we had to change the limit. That is, if x equals 0, u equals tan 0. So u equals 0. Okay, that's not so bad. 0 is still 0. That's all right. But then if x equals pi over 3, u equals tan of pi over 3. Oh, no. Special triangles. We thought that was over. Quickly, special triangle. Pi over 3, root 3, 1, 2. Tan of pi over 3 is opposite or adjacent is root 3 over 1. Okay, it's root 3. Whew! All right? So watch out for that. In a definite integral, you've got to keep an eye on the limits because those are x values, not u values.
Wouldn't we just find the antiderivative and then plug back in x and then?
Yeah, you leave these blank and go, I don't know. Just leave little x's here, little blanks there, and just go, I'll deal with it later. Integral antiderivative of u is 1/2 u squared. And then you're still stuck with leaving these blank. I don't suggest it, okay? But you could do that. You could just say, okay, well, I know those aren't, I can't put them there. I leave those blank out there, and then finish the whole thing off and go back to tan of x. So it's 1/2 of tan squared x, then sub them in, but it doesn't save you any work because you're stuck with doing it anyways. It feels like it's going to save you all this work, but you're stuck finding those values anyways. So that's why I suggest my method, because now it's, what do we do here? 1/2 root 3 squared minus 1/2 0 squared, and I think we get a pretty weirdly simple answer of 3/2. Oh, there it is. I was trying to find my last answer. Okay, while you're copying, I noticed I didn't give myself enough space here again, so I got to duplicate this page and then go back to there And there. I should have now 2 copies of this. Get lost. Clear the annotations on that one. I got this one. I got one more to go. Do you have questions there? One more to go, and I'll do it pretty quick. Okay? Because I think it's an easier one compared to the ones we've been doing. 0 to 1 of x over x squared minus 4. Okay. Let u equal x squared minus 4. du by dx is 2x. du equals 2x dx. Pretty traditional steps there. What I really want is x dx. So I solve for that. 1/2 du, oops, equals x dx. And what I get is integral from, okay, come back to that in a second. Sometimes I like putting little boxes here. I go, just to remind myself, you've got to put something there. You know, I got to think about it. And so what I get is x dx is 1/2 du, and this is 1 over u. Am I doing it fast to rush this lesson or to show off? Yeah, I'm showing off, but I think I'm showing off the method. It is possible, once you do enough of these, I'm sort of enforcing practice here, you know? If you practice it enough, this doesn't have to take forever, but you got to practice it, or else you won't be able to do it fast. Hi.
Hello. We got the emergency thing that they say.
They're the inserts.
Yes, thank you so much.
You're welcome.
Okay, talk about this limits of integration. They wanted x to be 0 and 1. When x equals 0, u equals -4. When x equals 1, u equals -3. So this is going from -4 to -3 now. Those are the u values that go with it. And what's the integral of 1 over u? It's a trap. Go. Ln absolute value of u. From -4 to -3. It has to be absolute value of u because 1 over u exists everywhere. So ln u has to try to exist everywhere. So we put the absolute value in there. And so I get 1/2 ln 3 minus 1/2 ln 4 equals 1/2 ln 3 minus ln 4. Maybe I could write it like this if I was really feeling. Lanny. She's not here. It's a good joke if she had been here. All these need practice, folks. They are not easy until you do a bunch of them. And then it's like quadratic formula, right? We keep talking about that. Seems like, what are you doing? And you try a couple, and away you go.